Hello. This lecture will cover pages 131 through 137 of my lecture notes. So please print out those pages and have them in front of you as I present this lecture on integrated circuit specifications, Part A, digital voltages and noise margins. We're going to start on page 131 in your lecture notes. This is chapter 7 in the latest edition of the textbook, or the textbook that I'm using. The terminology is common across all families, so whether you're using TTL or you're using CMOS or you're using NMOS, these specification abbreviations are identical. T sub A is operating free air temperature, V sub IH is high level input voltage, and V sub IL is low level input voltage. V sub OH is high level output voltage, and V sub OL is low level output voltage. We're only going to discuss in this lecture the first 1, 2, 3, 4, 5 types of specifications. I want you to notice something here as you read the VIH. It's always read from right to left. It's high level input voltage. Down here it's low level input voltage. Down here it's high level output voltage, and down here it's low level output voltage. You always read these subscripts from right to left. It'll be the same with the currents as well when we get into the next lecture. In order to go through this, we need to get out your manufacturer's data sheets. In particular, I want you to get page 173 in your specs. It's the quad 2 input NAND gate, and it's going to look like this. This is the specification that I would like you to get out because we're going to be using it. We will use the TTL or the T squared L. Sometimes people refer to this as T squared L logic family to investigate these specs. And then in homework you're going to be using other logic families and working with the numbers you find in the specifications for those integrated circuits. Before we start this, commonly used prefixes on page 132, I'd like you to make sure, from this point on in your career, you have to be using these prefixes. Tera, giga, mega, and kilo. And here's the magnitude that they represent. Notice that when you have a positive exponent on 10, it's a capital letter here. So you'll be using capital letter prefixes on units. And if the power of 10 has a negative exponent, it's a small letter. Milli is a small m, mu, n, in p. So tera, giga, mega, kilo, milli, micro, nano, and pico. And some examples are down here. As an example, 0.0015 amps. I do not want you to write it that way. I want you to refer to it as 1.5 milliamps. Instead of saying 0.00025 amps, it's 250 microamps, and 62 milliwatts, and 1 kilohertz, and 800 millivolts. This is the way I'd like you to refer to units from this point on. On page 133, why do they call the logic family TTL? Well, here is a NAND gate. That's a 2-input NAND gate, and here's the output, AB bar. And inside the integrated circuit, this is exactly how that is fabricated. Remember I said it has a multiple emitter input. There's 2 inputs, so it has 2 emitters. The outside circuit is referred to as a totem pole output, and we discussed this already. But they call it TTL because it has transistor logic stacked on top of transistor logic. Transistor logic. If you take a look at page number 34, T sub A is ambient free air temperature. We already discussed this before. 5400 series. Military grade, the spec is from minus 55 degrees C to 125 degrees C, and the 7400 series is commercial from 0 degrees C to 70 degrees C. If you look at page 173 in your specifications, you have that handy. I want you to take a look at this free air temperature right here, and you can see it right here in the specs. Notice T sub A is free air operating temperature, and here's your 5400, and here's the range, military grade, and here's your 7400, and here's your specification, commercial grade in degrees C. Voltages. Let's discuss voltages in digital TTL circuits. First, in the specification we're going to talk about in terms of voltages is VIH. It's high level input voltage and low level input voltage. These are input voltages. So when you see VIH and VIL, that I stands for input, and we're concerned about the input voltage here. Now, if you take a look at valid levels within a TTL range, here's 0 volts and here's 5 volts. And we said 5 volts was the ideal high, and we said 0 volts was the ideal low. However, you're going to find out in the specifications that these circuits don't work in an ideal mode. They work in a practical mode. So you're going to find out anything above 2 volts, from 2 volts to 5 volts, that's considered a good high to the logic circuit. It's a valid high input voltage. So as long as you have something at 2 volts and above on the input here, that IC is going to see that. Now, not only the NAND gate, but all the TTL gates we discussed, all 8 of them. They'll as long as the voltage is between 2 volts and 5 volts, they'll see this as a good high. What about low voltage? Well, as long as you're at 0.8 volts and below, as long as you're from 0 to 0.8 volts, that's a valid low input voltage. The invalid voltage range for TTL is from 0.8 to 4 volts. If you ever see a voltage between 0.8 and 2 volts, it's a good indication that something's gone wrong in your circuit. Now, with the exception of what we call tri-state output, but we'll talk about that later. But for now, anything between 0.8 and 2 volts are invalid. The gate cannot predict which state the gate will assume. We cannot predict which state the gate will assume if it falls between 0.8 and 2 volts. So if you look down here at the bottom, voltage IH, that's high level input voltage, has to be greater than 2 volts. It will be specified as a minimum value. VIL, low level input voltage, has to be less than 0.8 volts, and it will always be specified as a maximum value also. So let's take a look at the specifications. And if you look at the specifications, can you find VIH? I want you to find VIH. It's right up here. And notice VIH is going to be specified as a minimum value. There it is. And we're going to be looking at the 7400. We're going to be looking at the 7400 column here. It's specified as a minimum value of 2 volts. What about VIL? If you look at VIL, it's right here. And VIL is also specified, in this case right here, as a maximum value. And you're going to see why one specified as a maximum and one specified as a minimum in just a minute. On page number 135, we're going to look at VOL and VOH, low-level output voltage and high-level output voltage. When you see this O, we're referring to output voltages, referring to what voltage in the low state and what voltage in the high state this circuit will produce, or this circuit will produce, or this output, the output of any of the gates, because they all have totem pole outputs. If you take a look at these figures here, they'll explain what's going on. VOL has to be less than 0.4 volts, and it'll be specified as a maximum value. VOH, high level output voltage, has to be greater than 2.4 volts, and it'll be specified as a minimum value. What you're doing, if you take a look here in this particular part of the figure, this is the totem pole output of a gate. Let's say this gate up here, this NAND gate. And it's going to be driven in the low state. with the low state, this transistor's in, it's full on, it's saturated, and this transistor's in cutoff. That's how it goes to low. But because there's a voltage drop across that transistor, it's not ideally zero. And they're saying that that particular device, for a low level, it'll always be less than 0.4 volts. In other words, the drop across that transistor will never be greater than 0.4 volts for a low level. In the high level, if you take a look over here, this transistor Q3 is turned on. It's in saturation. And the lower transistor is in cutoff. So that allows this point to be pulled up. Well, it's not going to go to 5 volts, but they'll say, and it'll always be, the high level output voltage will always be greater than 2.4 volts. In other words, the voltage drops across that resistor and this upper transistor, and that diode will never be greater than, the voltage will never be, at this point, the point down here, will never be less than the 2.4 volts in the high state. It'll never be less than that. It'll always be greater than 2.4 volts at this point. So what's the significance of all that? What's the significance? Putting high-level input voltage, low-level input voltage, high-level output voltage, and low-level output voltage, putting those 4 voltages together. The reason we have these in the specification is so we can build a noise immunity. We're going to talk about noise immunity in the circuit. And before I go through the 2 examples with noise immunity, let me show you something here. If you have a wire and you stretch a wire across the room or across any open space, as long as that is a conductive, that can't be fiber optic cable, it has to be metal. As long as it's copper or it's aluminum, there's electromagnetic interference that bombards that wire. Electromagnetic interference, radio waves, the ballasts in the lights in the classrooms, motors that are running nearby, putting off electromagnetic interference. And what it does is it puts noise on this line. It puts noise on that line. That's white noise. Well, if you're driving a digital circuit, that could cause some problems. Let's say we have an inverter right here, and we want to put in a nice waveform that looks like that. And on the output, we want to get a nice waveform that looks like that. The inversion. Well, if you have white noise, which you do in all applications, you have noise riding upon this line. And on the output here, you have noise riding on that line. And if this is driving another circuit, and you expect it to be high, what about this noise riding on here? It's going to take the value down to a lower point. And if you expect it to be low on this line, this OR gate is going to expect it to be no higher than a certain value. That's where these voltages come into play. There's built-in noise immunity, and I'm going to explain that to you right now in specific. Very easy to understand. We're on page 136. Here we have a NAND gate that's driving an inverter. This line is low. When this line is low, the output, the low-level output voltage cannot get any greater than 0.4 volts. Keep that in mind. That's in the specification. That's why it's specified as a max. Low-level output voltage, the maximum it can be is 0.4 volts here. And what about the input voltage here? What's it expecting? The low-level input voltage max is 0.8 volts. So this is saying that this device here will recognize 0.8 volts as a low, 0.8 volts and below is a low. And this is saying that the maximum it'll put out for a low voltage is 0.4. So we can calculate a low-level noise margin for that circuit with noise riding along that low level. The white noise riding on that low level. The low-level noise margin is equal to VIL max minus VOL max. And if you make the calculation, every logic family, you can make a calculation for how much noise you can justify on that line or you can tolerate on that line without it interfering with that gate. I want you to, for TTL, for T squared L, look at the specification on page 273, and I want you to calculate the low-level noise margin for TTL. And if you do that correctly, you're going to see that the low-level noise margin, the answer is 0.4 volts. That's 400 millivolts. And then finally, if you look at page 137, what about the high-level noise margin? In the high state, when you're expecting 5 volts, we know noise is going to be riding on that. We know there's going to be noise riding on that 5 volts to dragging it lower. How much can you tolerate before this gets confused, before it drops down into that invalid region that I showed you in that graph a minute ago? Well, the high level output voltage is a minimum is 2.4 volts. That's saying that the minimum value that you'll see here on the output of a totem pole TTL gate is 0.4 volts. It'll never, if it's working right, it'll never be 2.3 or 2.2. It'll always be 2.4. That's the minimum. This is expecting 2 volts. What does this have to see in order to see a good high in the high state? Well, the high level input voltage minimum is 2 volts. So if this is saying this will never go below 2.4 volts, and this is to put out a good 1, and this will recognize a good 1 clean down to 2 volts, then you have a built-in noise immunity, which means you can have noise riding on the 5-volt waveform. Or in this case, you can have noise riding on the 2.4 volts that this device may put out. Because it's not going to put out, ideally, 5 volts. It's going to be somewhere between 2.4 volts and 5 volts on the output. The high-level noise margin is equal to VOH min minus VIH min. Just a simple calculation. These equations that I just gave you for high-level noise margin and low-level noise margin, they're the same equations used in every family. CMOS, PMOS, NMOS. It's just the specifications change. We're working with TTL. So I want you to look at your spec on page 273 for the quad NAND gate package, and I want you to calculate the high-level noise margin. If you do that, and you do it correctly, I'd stop the video and see if you can calculate it. You should get, the answer is the high-level noise margin is equal to 0.4 volts. That's 400 millivolts. Now, it turns out that the low-level noise margin and the high-level noise margin are both 400 millivolts. They're not always the same when you get into other families, or if you have one family driving another family. For instance, if this was a CMOS device, and for some reason you have a CMOS driving a TTL, these noise margins will change. So you have to use these formulas. If this was CMOS, you'd have to use a CMOS specification for VOH min. And if this right here was TTL, you'd have to use the TTL specification for VIH min. In your textbook, I'd like you to take a look. There's an example 8.1. See if I can't find it here. This is the example. You can locate it. It's example 8.1. It says the input-output voltage specifications for the standard TTL family are listed in table 8.1. These values, use these values to determine the following. And you want to find the maximum amplitude noise spike that can be tolerated when a high output is driving an input, and then you want to find the maximum amplitude noise spike that can be tolerated when a low output is driving an input. And all they did was put this particular table, just takes the specs right off of the page 273 in the National Semiconductor specifications that I gave you. And here's the solutions. Make sure you understand how they get those answers. And that concludes the lecture.